Microwave Engineering Lecture 2, Telegrapher Equations for the Transmission Lines and also Power Flow. Please refer to the figure shown here. So this is a microstrip. Microstrip is one method for making electrical connections in a microwave circuit. So it is constructed with a ground plane on one side of the PCB. So you see here underneath here, this will be the ground plane, and then you have the dielectric substrate. So the dielectric substrate will be of any permittivity. So it is denoted by this symbol here. So E. E would be the permittivity, and it also have the loss tangent. And then you have the land on top of the dielectric substrate, or usually we would call it as patches. So the patch would be the transmitting signal. Microstrip is an example of a transmission line, though technically it is only an approximate model for microstrip. So why transmission line? Imagine two ICs that are connected as shown in the figure. So you have A and also B. So when the voltage at A changes state, the new voltage at B would not appear simultaneously, instantaneously, because these 2 points are separated by a large electrical distance. So when it is separated far away, there will be a propagation delay. So that's why it wouldn't be an instantaneous effect. In microwave circuit, even very little distances, as a few inches, would be considered very far, and the propagation delay for a voltage signal to appear at another IC would be significant. So this propagation of voltage signal is modeled as transmission line, or we denote it as TL. So later on, we will see that the voltage and current can propagate along the transmission line as waves. So we usually call it as propagating wave. So the TL model can be used to solve many types of high frequency problems. You can solve it in coaxial cables, in two wires, in microstrip, straight line, coplanar waveguide, and so on. So all these transmission lines would share one common characteristic, which is the electric and magnetic field are all perpendicular to the direction of propagation. So let us see an example of a transmission line here. So this is the coaxial cable. So on the TL, the voltage and current vary along this structure in time, T, and especially in the Z direction. So Z direction will be this way. A common circuit symbol for the transmission line will be the two-wire parallel symbol. So if you see the figure down here, this would be the two-wire which is parallel to each other. So this is the circuit symbol for the TL. It will indicate any transmission line. Now, analysis of the transmission line. So the TL, voltage and current would vary along the structure in time, T, and also the distance, Z, as indicated in the figure. So there will be no instantaneous effects. There are delay. So how do we solve for V and also I in this figure? So first, you need to develop the governing equations for the voltage and also the current. Then only you can solve the equation. So notice in the figure, there is a conduction current in this center conductor. and also the outer shield of the coaxial cable. And besides that, you also have the displacement current, which is between the two conductors where the electrical field is varying with time. So each of these currents has an associated impedance. So you have two, the conduction current and also the displacement current. So conduction current affects the resistance and also the inductance. So resistance is affected due to the losses in the conductors, while inductance is due to the current in the conductors and the magnetic flux in the current path. Next, you have the displacement current, which will affect the conductance and also capacitance. So conductance is due to the losses in the dielectric between the conductors, while capacitance is due to the time varying electrical field between the two conductors. Now we are going to consider only a small section of delta Z of the transmission line. So this delta Z is very small, that the electrical effects are occurring instantaneously, and therefore we can simplify using the circuit theory. Okay, so this equivalent circuit is shown below in figure 2. So that's why you are denoted by all the delta Z at R, at L, at C, and also at G. So the variables, which is R, L, C, and G, are distributed or PUL per unit length with units of ohm per meter, and then you have the H per meter, F farad per meter, and also the Siemens per meter respectively. So we will sometimes ignore the losses in this course. Now, a finite length of the transmission line can be constructed by cascading many of the subsections along the total length of the transmission line. So you can have the same figure over and over again, cascading many of the subsections depending on the total length of the transmission line. So in the case of a lossless transmission line, which is an ideal case where the R, the resistance, is equal to the G, which is 0. Okay, so there are no loss. Okay, it is lossless. So this cascade will appear as this because you are ignoring the you are ignoring any losses. So the R is without any delta. So this is the general model. It applies to any transmission line regardless of its cross-section shape, provided the actual electromagnetic field is TEM, the transverse electric magnetic.